this going to be recorded? Okay, I can see already the symbol. Okay, perfect. Well, so for me, it's a pleasure to introduce to you our speakers today. Stefan Rosbach is a professor of astrophysics in the Department of Astronomy and the Oscar Klein Center at Stockholm University, Sweden. He's interested in the multi-messenger astrophysics of compact objects, with particular emphasis on their fluid dynamics, nucleosynthesis, and electromagnetic transients. In particular, he's an expert in numerical simulations of compact binary mergers. He's also well known for his work in advancing several technical aspects of smooth particle hydrodynamics, as well as for his pedagogical reviews on this topic. He has published more than 170 articles that have collectively been cited more than 12,000 times in the specialized literature. And without further introduction, the mic is all yours, Stefan.
Okay, thank you very much for the nice introduction, Emilio. I will then share my screen. Go for this one. So can you see that again? And also the mouse?
Yes.
Yes, we see it.
Okay. Okay. Then well, I just start. So I will talk a little bit about multi-messenger signatures from neutron star mergers, and I will. Well, since this is for a relatively specialized audience, I will also talk about some recent developments that we had made. And maybe just as a side remark, I have been offline, off work for a couple of weeks for private reasons. And therefore, I'm not, well, some of the results I had hoped I could present are not yet ready. So we'll just talk about the recent developments. So let's do first things first. So just a couple of very basics. Of course, all of you know that neutron stars are born in supernovae. We know thousands of them. And we have of the order 20 binary systems where actually both stars are neutron stars. And their structure is shaped essentially by all fundamental interactions. It's by strong gravity, by strong interaction, but also weak interaction is important in determining the composition, and also the Coulomb interaction to get the crust of the neutron stars. And if you solve theoretical models, then they may look something like this, that the crust contains iron-type nuclei. Then you have a bulk of relatively conventional material of neutrons, protons, electrons, and muons. And in the core, you may have more exotic material. And since this will pop up a couple of times, I just want to introduce this quantity of electron fraction. And you can just think of this as the number of protons per nucleons or the number of electrons per nucleons. Now, one of the first systems that was actually discovered of neutron stars was a binary system. And interestingly, already this first binary system was a system where the second component is also a neutron star. And this system has turned out to be very, very influential just because it gave us, for the very first time, a very strong indication that gravitation waves really do exist, because the orbit was seen to in-spiral, and it was therefore very influential in motivating the direct search for gravitation waves, like with the LIGO and the Virgo detectors. And the discoverers were awarded with the Nobel Prize in 1993. Now, if you take this seriously, then neutron stars will at some point collide with each other. And what I'm showing here is a simulation, which is actually a real collision. So it's not a gravitation wave-driven merger, but a real collision. And I just want to stress how extreme the physics is that is involved in such a neutron star merger. So if you just think of it in terms of the composition, and I will compare against the sun, then the sun contains about 85% protons, while a neutron star is only containing about 5% of protons. Then, of course, as all of you would expect, gravity is strong, and a measure of that is this dimensionless mass over radius ratio, the so-called compactness. And for a neutron star, that is about 0.2, so something like 20%. While for the sun, this is only 10 to the minus 6. The densities, just keeping in mind, a typical neutron star has of the order 1.4 solar masses. and a radius of about 12 kilometers. And that tells us, well, the density is substantially above 10 to the 14 grams per cubic centimeter, even the average density. And in the core, it may be maybe even an order of magnitude more than that. And this is, of course, gigantically much more than what you have in the sun. The sun has about 1 gram per cubic centimeter, which is about approximately what water has as well. Then if you have such a collision, then you expect temperatures well in excess of 10 to the 11 Kelvin. And again, in the sun, you have about 10 to the 7, so about 10,000 times more than in the core of the sun. And since I've said the densities are very large, this has, of course, implications for the dynamical timescales. And for neutron stars, they are below actually milliseconds. So a timescale on which a neutron star can substantially change its shape is of this order sub-millisecond, while the sun takes about an hour or so. And if you compare the neutrino luminosities that you have in such a merger, they are of the order of 10 to the 53 ergs. And that is about, in neutrinos, that is about 20 orders of magnitude more than what the sun is emitting in photons. And now if you take all of these things together, say the densities and the temperatures, then you also realize that weak interactions become very fast. And just as an estimate for the time scale, if you have something like the electron fraction over the change of the electron fraction, that gives you also a time scale which can be of the order millisecond or sub-millisecond, so very much comparable to the dynamical timescales that we have. Neutrinos are the only ways in which such a merger remnant can cool, at least on dynamical timescales. And treating neutrinos is actually pretty difficult compared to many other astrophysical scenarios, just because in the centers of those remnants, matter is pretty much completely opaque to neutrinos, while the outer layers are completely transparent. So you really have to do some proper transport, and it depends really on the exact question that you're asking, how accurate that needs to be. So as probably all of you know, or at least most of you know, it's not only interesting just from this extreme physics point of view, but it's also very interesting because these systems are related to lots of very exciting questions. And just the fact that we have a couple of these systems tells us already quite something about binary evolution. Then I have briefly alluded to these high densities. We can learn something about constrain the properties of nuclear matter there. One of the major science drivers behind studying these systems is, of course, the detection of gravitational waves. And it has actually been already realized in the 80s by Bernard Schutz that you can actually also use them to get the luminosity distance and to actually do cosmology with them. And then one topic that is actually pretty close to my heart is the idea that they can form heavy elements. And I will say a few words about that. And just as a side remark, this was considered as very much exotic, or by some people even as crackpot physics for a couple of decades. But it seems now that this was actually true. And if this is true, then this is related to the enrichment of the cosmos with heavy elements. And these freshly synthesized heavy elements should produce radioactively powered transients. These are the things that are called macronovae, or by some people kilonovae. And they're also supposed to produce short gamma ray bursts. That was also speculated since the 80s. And now in 2017, we had finally this wonderful event where both gravitational waves and electromagnetic waves were detected. And that event really connected all these different areas and really confirmed all these long-held suspicions. And some of them were really puzzles for half a century, like, for example, the heavy element formation. Now, just briefly to recap what we have learned. Well, one thing that we had learned was that they actually really do produce gamma ray bursts. So the Fermi satellite saw this gamma ray burst, while LIGO detected this chirp signal. And the punchlines there were, well, of course, they actually really, as expected, do produce gravitational waves, but they're actually maybe more interesting or more, well, less questionable, they actually also do produce short gamma ray bursts. Now, maybe one of the most interesting results that was coming out of this multi-messenger follow-up was that this event was actually also seen in electromagnetic waves. And most importantly, the host galaxy showed here at about a day after the merger this blue signal, while a couple of days later this turned into a red signal. And I just give the interpretation away, of course, from the beginning, since probably most of you know this. So the interpretation here is that here you have relatively low opacity material, which is caused by the nucleosynthesis of matter that has an electron fraction above a value of 0.25, so just about a quarter of protons. While this material is produced by a matter that has a substantially lower electron fraction and a really low by most other stellar standards. Now you can ask, well, can we really be sure that this was really powered by radioactive decay, and especially these rapid neutron capture elements? And I think we can be fairly sure that this is actually the case. And just to illustrate this, this is a little experiment that I had made just when this discovery was made. And the idea here was that you take a sphere of gas and let it expand. And you solve a nuclear reaction network in this expanding gas. And you vary the initial electron fraction and the velocity. And what you find then are the heating rates. That is what you can measure, just the radioactive heating rates that you get. And this is shown by all of these lines. And what you see as the observed luminosity, so these are those yellow dots, so well, gold coins, or however you want to call them. And you see now there is a bunch of these lines that fits actually pretty well with those observations. And interestingly, well, these are the special conditions that produce rapid neutron capture elements. So you see there's a range of them, but as long as you get our process, then you fall very nicely on this observed line, while higher electron fraction trajectories produce something very different. Now, there's another actually also very interesting indication, and that indication is that Watson et al. Identified strontium lines in the electromagnetic transient. And this is interesting because strontium is actually a pretty light R-process element. And it was, if you would have asked people beforehand, what would be the elements that you, well, would potentially be produced or likely be produced, then I guess strontium would not have been the first one that people would have mentioned. So what we have learned from that is, I think it's very fair to say that very likely what we have seen is actually really powered by rapid neutron capture elements that are decaying. And a very interesting implication of that is both of this blue to red transition and actually also of these strontium lines is that it is actually a very broad range a very broad range of electron fractions that is responsible for this. And this, and I will explain this a bit more in detail a bit later, this is actually telling us that weak interactions have been crucial in shaping this material inside the neutron star merger. Now, if you've looked or listened carefully, then you may have realized that I've cheated here a little bit in this plot because I'm comparing a bit apples with pears. On the one hand, I'm comparing luminosity, so energy per time, with a nuclear heating rate, which is an energy per time at mass. So there's a mass somewhere hidden. And what I've put in here is a mass of 1.5% of a solar mass. And that means if we could observe all the energy that is produced by the radioactive decays, then you would need at least 1.5% of a solar mass being ejected. So in reality, that means, well, you have probably a factor of a few more than this 1% or this 1.5% of a solar mass that was responsible for this. Now, this multi-messenger event was really actually everything we could ever have asked for. It was gravitational waves, it was a gamma ray burst, we knew the host galaxy, the electromagnetic transients, the Hubble parameter was determined. a very interesting result was that one could show that gravitational waves propagate at pretty much exactly the speed of light. There were constraints on nuclear matter, and there was this electromagnetic transient, which actually really showed that at least a major portion of the heavy elements in the universe are produced by neutron star mergers, and maybe actually even all. But I guess the more likely thing is that it's just a major fraction. And all of this progress came essentially from the combined gravitational and electromagnetic wave detection. Now there are different things that can be learned from both of them, and it's different physics that determines them. So the gravitational waves, they carry essentially the imprint of the system that is merging. So it knows about the masses and the spins and the tidal deformability. And the physics that determines it is the hydrodynamics, the strong field gravity, and the high density matter, while the electromagnetic emission is telling us a different story. It's telling us about the host galaxy. So it tells us about the astrophysical environment. It can tell us about the redshift, and also the physics that determines it is a very different one. So it is the weak interactions that determine the neutron to proton ratio. This in terms sets the nuclear reaction. Then the resulting elements, well, you need their atomic structure and radiative transfer to then be able to make really predictions how this looks like electromagnetically. And one point that I really also want to make is that here you are determined by really bulk motion of the material. And for example, the composition of the material that you're talking about has a relatively minor impact as long as it doesn't change the equation of state too much. While the electromagnetic emission is essentially just coming from a very small portion of the merging object here. So it's about, we are talking about 1% in order of magnitude that determines all of the electromagnetic emission. And here the composition is really, really crucial. So what you can observe depends very sensitively on the exact, atomic structure and what the stuff is made of. So here the composition is really the crucial thing. And if you think of this in terms of modeling such events, then you also may want to choose, or maybe potentially different methods, depending on which question you're asking, whether you're more on this gravitational wave side or maybe more on the electromagnetic side. Now, this is a major challenge for modeling, as you can imagine. Well, we know something about 10 kilometers in milliseconds, and the other part of the story that we know is happening at 10 to the 15 centimeters and timescales of weeks. And of course, you would want to know what is happening in between. And I think it's fair to say that at least in the very early interpretations of this multi-messenger event, which of course had to happen under an enormous time pressure, many relatively simple models have been used, and I think they did a good job in the first interpretation of this. But in practice, or in principle, there is a fair amount of physics that is really connecting these two types of signatures. And think of what's happening here at the merger. So if you do your best numerical relativity simulation with nuclear matter, hydrodynamics, your best neutrino transport, magnetic fields, whatever, you name it, this will then give you the amount of material that's ejected, the velocity structure, the electron fraction. Once you have this, you can start running your nuclear reaction networks. Once you have them, then you can start modeling the expanding cloud, which is powered by the radioactive decay of whatever has been produced here. And then once you know the atomic structure and have the line information, then you can do radiative transfer simulations to really make this prediction. As you just see from this list here, this is a very challenging endeavor. And we in Stockholm here, we try to make progress in really connecting these two things. But it's of course a bit of a long-term project, which contains lots of challenging ingredients. So let me now briefly come to this question of rapid neutron capture or R-process nucleosynthesis. So if you look at the solar system, then you see from a plot like this that you have to form the heaviest elements by neutron captures. And if you look carefully at these features here, then you see there are these double peak features. And that tells us that nature is working within those neutron capture processes essentially in two modes. One is a slow mode, which produces this peak to the right, which can be explained by nuclear physics, why it's to the right. And then you have a rapid neutron capture process, which produces a peak to the left of this S process. And this rapid neutron capture, or R process, is what we're talking about here, and that is responsible for about 50% of the elements that are heavier than iron. So we're not just talking about a couple of exotic elements, but we're really talking about a major part of the heaviest elements that we know about. The idea where this would happen has been discussed a long time ago, and that's why I said half a century are some of the questions old. And Burbage, Fowler, and Hoyle, and independently Alistair Cameron, realized in 1957 already the major mechanisms, how these neutron capture processes work. But of course, they had to speculate where they could happen. And of course, at that time, the most natural thing to speculate about was that they would be in supernovae. And this idea has actually stuck in the community for really decades. And that's also what you can still read in many of the textbooks. But it was never really proven. And therefore, in 2003, there was a National Research Council committee report coming out, and it identified the question of these heaviest elements as one of the 11 science questions for the new century, just because it's really a big and until then unsolved question. Now, in '74, David Schramm and James Latimer published a paper, and I had talked with James Latimer, and he told me that David Schramm had heard from the Princeton group about the Hulse-Taylor discovery, and he was wondering whether such a thing could do anything for nucleosynthesis. And for purely technical reasons, I believe, they did not look at a binary neutron star case, but at the neutron star black hole case. And what they found is that this could potentially be very interesting as an R process site. And they tried to estimate the amount of ejecta that you could expect from there. And their conclusion at that point was, well, it could be something like 5% plus minus 5%. So it could potentially be very interesting, but it was not entirely clear whether it actually would be. So there was a question mark, is this really something that is happening or not? The first hydrodynamics plus nucleosynthesis calculation then took some longer time. So that came then in the late 90s. And there we found actually that typically you eject something like 1% or slightly more of a solar mass in very neutron-rich material. So this is one of these very first calculations where you see the ejecta here in red. And we also did nucleosynthesis calculations for that. And that turned out to actually very nicely reproduce the solar system pattern, which is shown here as the crosses. And in particular, it just produced for free this peak around platinum, which is at a nucleon number of 195. And just to put this into a perspective, for all of the supernova calculations before, this was always the major challenge, and people had to increase the entropies in their simulations by something like 500% to just get close to this region here. And here it just came out with essentially every trajectory. It produced this without really zero tuning. And this idea then was now finally then confirmed with the first multi-messenger gravitational wave detection in 2017. Now, if we take this idea a bit, if we take this serious and say, well, let's have a look at, we now have some indication what electron fractions we need, then it's of course an interesting question to ask, well, what is actually in the original neutron star? And what you can do then is you can calculate what is the beta equilibrium electron fraction as a function of density and temperature. And say for all neutron stars, the ones that are in spiraling, you are of course interested in the very low temperatures, so down here, and you have very high densities, so somewhere around this region here. And there you see the electron fraction under these conditions is in equilibrium, something like 0.05 or so. And you can do this now, of course, a little bit more careful if you want. You can just construct the neutron stars or pick your favorite nuclear matter equation of state, solve your Oppenheimer-Volkoff equations in beta equilibrium, and then you can produce a plot like this. It's a bit complicated. That's why I want to explain it a bit. So let's maybe focus on this black curve here with 1.4 solar mass neutron stars. And this is one particular equation of state. And what this shows is the fraction of material that has an electron fraction above the value given below. So that means where we start here, well, everything has a fraction of 1 because everything, the whole neutron star, has a non-zero electron fraction. But then if you go to this point here, for example, this black point, then you see that tells us, well, only about 10 to the minus 4 of the neutron star has an electron fraction above 0.07. So that means essentially the whole neutron star is, well, in this region here below. And as I had said from this multi-messenger observation, we have very good reasons to believe that the electron fraction that we have seen in a substantial fraction of the material must be larger than 0.25. But that means the original neutron star practically does not contain this material. There's only, in this beta equilibrium, there's only something like 10 to the minus 5 of the matter in this electron fraction. And the fact that this has been observed tells us that what we have seen was really weak interactions at work. And if you want to get the answer right, then you need to solve these two things together. Then you need to get the dynamics of the merger right together with a proper neutrino treatment, or at least a decent approximation to it. Now, I had said we had seen these early ejector cases and that it produced these heavy elements. But from today's perspective, that was just one of the ejector channels. What we were talking about was that stuff that we see, for example, here in those tidal arms. Now we know there are more such channels. There's also, when the stars come into contact, you can shock heat some material in the polar regions. A very important ejection channel are neutrino-driven winds. That you have such a merger remnant. And as I had said before, this emits about 10 to the 53 ergs per second in neutrinos. And some fraction of these neutrinos is actually absorbed here in these inner regions of the torus, or maybe the outer layers of this hypermassive neutron star, and it's just blowing out a wind. And this wind has actually pretty different properties from these tidal dynamic ejecta here. And then you have a third class of ejecta, which are called secular, because they are ejected on timescales which are substantially longer than those guys here, of the order of a second. And this is likely a very important channel because it probably contributes a large amount of material, something like 30 or maybe even 40% of the initial torus mass can become unbound. But at the moment, there's no consensus yet what type of material this would really be, say in particular what the electron fraction of this material would be. And I will say a bit more about these neutrino-driven winds now. I've just explained the mechanism. And this is from some very nice work that was done during the PhD thesis of Albino Perego. And you see here in particular, you see a snapshot at 84 milliseconds. And maybe just focus on the left panel here. What you see here is the electron fraction. And you see that this is very much different from this 0.05 that we expect for the tidal ejector. And here you have a broad range, which may be something like 0.2 and about 0.4. And the change is, of course, coming from absorbing mostly neutrinos and maybe to some extent closer in also due to positron captures. Now, if you look at the nucleosynthesis of these different things, so the left side here shows the dynamic ejector, the right side shows the neutrino-driven wind ejector, then you see initially all of the action is here at this neutron trip line, so in the extremely neutron-rich regime. Then you produce very, very heavy nuclei, which also do some fission cycling and fission some material down here. and in the end, everything decays. And then you see something which is very similar to what I had shown from these very first calculations. Here again is this platinum peak. So you produce a lot of material above something like 130 and not terribly much below. Now, for these neutrino-driven winds, that looks very different. First of all, you're not starting at the drip line. You're still very neutron-rich, but not at the drip line. And you're never reaching this regime here. And once your neutrons run out and you're just left with the radioactivity and the matter decaying, then you see as things are decaying back, you produce a very different pattern, but which is actually nicely complementary to the pattern that you see for the tidal dynamic ejector here. And if you compare the two things here, so these are just kind of like the end results, then you see here you produce these heaviest elements for this tidal ejector with a very low YE. And it's essentially each time the same pattern that you see. While for these higher YE elements, you produce, well, a complementary part. And maybe I should have said this here. Those blue things are the solar system abundances, while the curves are the simulation results. And you see this nicely complements these tidal ejector, but it's also much more volatile. So you see every trajectory produces a different composition, while here it's essentially all the same. Even if you take different mass ratios of neutron stars or take a neutron star and a black hole, as long as the YE is very low, you get a very, very robust pattern. Now, this is, of course, then very interesting because these guys here in this lanthanide region, so that's the stuff that you produce here for this very low YE material, they're very important because they produce very high opacities and therefore make it difficult for produced photons to escape. And this is the idea why we think this type of material produces the red emission, while that stuff here produces the blue emission. Now, once we have had a merger, then in a cartoonish way, it may look something like this. In most cases, you likely produce a hypermassive neutron star in the core, surrounded by some type of torus. You have in the equatorial plane, you eject some extremely low YE material, which produces well, very neutron-rich ejector and this strong R process, while these neutrino-driven winds, they can blow out weak R process material, which is still R process, but lower in mass, and mostly along the rotation axis. Then in many cases, the neutron star may collapse and form a black hole, and then likely could produce a gamma ray burst jet. And one of the questions that you may want to ask now is, well, what is actually the impact of such a jet on the macronova signal that you would expect from such an event? And this is not really just a question that we try to investigate, or well, mostly Lorenzo Nativi, who is a PhD student in Stockholm. And the question was exactly this. Let's start from the neutrino-driven winds that we have from Perigos et al. Simulation, and then shoot a relativistic jet through that and try to understand what a possible impact that could have on the radioactively powered electromagnetic emission. So just practically, this is actually a pretty long chain of simulations, and some of them, looking at them now, seem already pretty old. So we had started this whole thing with merger simulations with a smooth particle hydrodynamics code, and that contained a neutrino leakage scheme and the nuclear equation of state. That is actually already from 2007. And the final products of these simulations were used by Albino Perego in his PhD thesis, where he then tried to look at neutrino-driven winds. This was then done with Eulerian code, which is called FISH. And the major reason for using this was that this code contained a more sophisticated neutrino treatment, and in particular, it allowed for neutrino absorption so that we can really see winds that are emerging. So from these simulations, we get then snapshots of how the winds would look like after of the order 100 milliseconds. And this is what we then have taken for yet another code and as initial conditions. And we place a relativistic jet into this. And for those, some of you, I know some of you are doing simulations themselves. So this is a code called AMUN, and this is a special relativistic adaptive mesh refinement code. So it's actually pretty similar to the Pluto code that some of you may know. but it's written somewhat differently. And we follow here the matter until it is close to being homologous. And then once this has happened, we map this again in a three-dimensional time-dependent radiative transfer code, a Monte Carlo code, the POSIS code written by Mattia Bulla, and to get the radiative signatures out of that. Now, maybe just to fix the ideas, how this looks like. So this is just an example of one such simulation. So what you see here is the density. And you will see here, it's not the beautiest movie in the world. And the reason is that the scales are changing pretty dramatically. So we had to do several remappings during the evolution. And you will see that while I let this go. So you see now the jet breaking out of this neutrino-driven wind and moving away from the remnant, which of course would be here in this, along this X-plane. And you see now the jet being pushed out and it's shutting off at about 100 milliseconds. And that's why you see now matter is starting to fill in this material here. And we keep expanding this until we are close to homologous expansion, just because the radiative transfer code is assuming homologous expansion. Now, what is special about these conditions? So I think this has been looked at in the literature before, but to my knowledge, not at this detail. And in particular, in most cases, the initial winds were idealized as spherical blobs of material, while here we try to really take whatever we get from Albino Perregos's simulations. And this has two important impacts. One of them is you have a very low YE layer at the leading edge of the wind. And the other thing, which is actually a bit annoying for the person who has to inject the jets, is that you have some initially pretty strong downflows here along the rotation axis, and therefore you have to keep pushing the material for quite a while. So maybe let's not go too much into the details here. So the punchline here is, and maybe let's start here at an opacity map. So these are the opacities, and you see if you don't have a jet, so just a wind, then the opacity is pretty much spherically symmetric. This is a reason because we had injected the secular ejector in a spherical way. But if you see if there's a jet emerging, then this punches a hole into this high density ejector. And you see these are different types of jets, and the hole becomes bigger if the jet is more energetic. And just for an observer, this would have the impact, maybe I should say this also. So these are absolute magnitudes in different bands. This is the time of the merger, and color-coded in these lines is the viewing angle, so that the red stuff is what you would see along the orbital axis, along the orbital plane, and the blue stuff is along the orbital axis. And the punchline is that what this jet majorly does is it makes the transient bluer if you see it from the jet rotation axis, and more so if the jet is more energetic. And the reason is, just in this cartoonish way, is essentially just that you keep punching away this high opacity material, which is sometimes referred to as a lanthanide curtain. So you're just punching a hole into this, and the radiation can escape then from there. And it looks bluer if you, and brighter if you see it along the jet axis. Now, this has a couple of implications. So once more, I've said it before, I think clearly, so it once more say the weak interaction is very crucial to get this right. And now one question that you may ask is, well, is this actually a real thing, this high opacity skin? And of course, we were asking this ourselves, and our referee was actually also asking this. And we think actually there are very good reasons that this may be there. And the reason is just the neutrino luminosity takes the time to ramp up. So the first material that you eject, that flies out without being in a terribly tremendous neutrino bath. But as time goes on, maybe on a time scale of 10 milliseconds or so, the neutrino luminosities keep increasing very, very substantially. and the matter that is closer to the source will capture the neutrinos and therefore get more proton rich. And therefore, I think it's perfectly plausible that you have this skin that is seen in Albino's initial conditions here. Now, just as a kind of corollary of all of this is, this seems like a actually pretty small detail, because this skin is a very small amount of material. It's just something like 10 to the minus 5 solar masses or so. And it tells us that this can actually already have an impact on the observed signal. And therefore, I think it's fair to say that we think we would expect a very large variety of different macronovae that we would hope that will be observed, hopefully soonish again. So I will leave this topic now here. And since I think we're relatively informal here, I would just want to show a couple of new developments that we have done recently. And two are related to hydrodynamics, and in particular to Lagrangian hydrodynamics. One is a very high accuracy smooth particle hydrodynamics code, which is called MAGMA. And many of the things that have been learned in this type of test bed have now been translated into what I think is the first Lagrangian full GR hydrodynamics code. This is a thing which is called Sphinx BSSN. And for the experts among you, this BSSN stands for the way in which the space-time is evolved. And Emilio has been very important in getting the Kerr version of that, but that has unfortunately not yet been published. And promise to Emilio, this will happen soonish. So, and then the second part where I just want to give the baseline, because it's actually even a bit more technical, is we have worked very hard on a new way to treat neutrinos. This is a so-called spectral leakage scheme. So we look at different energy bins of the neutrinos, and that has been gauged particularly for neutron star mergers. And we have compared this to what I think at the moment is the state of the art for a full simulation, which is a so-called two-moment scheme, or M1, and an even more expensive scheme, which can just be done on snapshots. But we have also compared with this, a Monte Carlo code called Sidoniu by Sherwood Riches. And the punchline of all of this, and this is the very hard work of my PhD student, David Egizi, is that we can get the same accuracy as such an M1 scheme, but without substantially increasing the simulation time. So here, all of the neutrino time is slightly less than what the hydrodynamics takes anyway, while in these M1 schemes, you typically spend 90% of your time on the neutrinos, which means if you have finite computational resources, that means, well, you have less resources to resolve the hydrodynamics. Let me now very briefly talk about these things. And I'll not go into the technical details, I'll just mention them. And those of you who have interest in those simulation techniques, I would want to encourage to have a look at the code paper. There are also lots and lots of challenging tests, and many of them have never been shown for smooth particle hydrodynamics. If you're interested in this, just please go ahead. The punchline is, it is smooth particle hydrodynamics. So we model the gas by particles that can move around freely. It is formally smooth particle hydrodynamics, but it has many elements that I have borrowed from finite volume hydrodynamics techniques. And I'll say a few words about that on the next slide. And the nice thing is it keeps all the things that, well, the SPH users love about SPH. That is namely exact conservation, exact advection, and natural adaptivity. So the particles just go where the matter wants to go. But many things are substantially more accurate than in standard SPH approaches. And I will show just one example of this. So just the punchlines. The gas is modeled as particles, and each particle carries a smooth kernel function with it. And the the ingredients that are now new are that we use different kernels, so very high order kernels due to some mathematician called Holger Wendland. They make a very big difference. Another very important difference is that gradients are calculated in a very different way. Normally in SPH, you just calculate them by taking kernels of these, taking gradients of these kernel functions. But in Magma, I'm doing this by more sophisticated matrix inversion techniques. And that can, in test cases, make the gradient estimation something like 10 orders of magnitude more accurate. Then there are new developments in terms of dissipation. And one thing is, I know people like Fabio, for example, work a lot with finite volume techniques. So I'm doing here very similar things. This code uses still something called artificial viscosity, but which is actually very similar to an approximate Riemann solver. And in these artificial viscosity terms, we do very, very similar techniques to what is done in finite volume techniques. So we're doing a reconstruction that is slope limited to avoid overshoots and so on and so forth. And this makes already a huge difference in reducing unwanted dissipation. But you can actually do even better. And this is what I mean by this entropy steering here. There is one parameter in this one, which is typically just set to 1. And I actually want to do even better than these reconstruction techniques. And therefore, I want to evolve this parameter. And the basic idea of how to evolve this parameter is now really very physically motivated, I think, because what we want to model is an ideal fluid. And that means it's a fluid where every fluid parcel conserves its entropy. And this is not enforced by anything in the code. So you can use this as a measure of the quality of the flow. And you can then just look at if a particle is moving around, how well conserved is its energy. And it could be that maybe the particle does not conserve this. Then the reason would be it's either running into a shock, or maybe the particle distribution becomes noisy for some reason. In both of those cases, you would want to add some dissipation, but the right amount. And you can actually really do this by this non-conservation of entropy. And that works very, very nicely and doesn't cost actually anything at all. So I just show, as I said, a couple of examples. The technical details can be found in these 2 code papers here. Maybe just start with a standard test. So this is a 3D set of Taylor explosion, one of the standard examples that probably most have seen in gas dynamics courses, and one of the standard tests for a hydrodynamics code. So you see here this strong explosion expanding in a low density environment at different times. And just by eye, you see there's probably exactly 0 deviation from perfect spherical symmetry that you can see. And another thing that you probably do not see is the analytic solution is actually overlaid. So this is this leading black line here, which is the exact solution. If you look at this as a function of resolution, so this is 64 cubed particles, this is 256 cubed particles, and I'm really showing every single particle, and you see there's hardly any noise visible. And for all, if you do such simulations yourself, just check this for your preferred code. Both Eulerian and Lagrangian codes usually show a lot of noise here in this post-shock region here, but this is essentially just gone here with these Magma results. I will now only show 2 more tests. One is in particular because this keeps popping up again and again. This is a Kelvin-Helmholtz test where you say you have a high density region moving in this direction, you have a low density region moving in the other direction. And that means here you have shear interfaces, and they should become Kelvin-Helmholtz unstable. And this is something where, at least in the linear phase, one has an analytical growth rate, and one can compare how good different codes agree with this analytical growth rate. And part of the motivation why I wanted to show this test is also because there was a serious code paper from 2012 by Colin McNally, where they compared how well different codes work with a specific Kelvin-Helmholtz setup, and they use as a guideline the pencil code from actually my colleague Axel Brandenburg in Stockholm. And they compared different codes, and many of the grid-based codes were very good at this, but standard SPH produced, well, these wimpy growth rates grew too slow and or maybe not even at all. And therefore, I wanted to test how well magma performs in this case. And I'm showing now the dynamical result here. So you see the density to the right, sorry, to the left, and you see my dissipation parameter to the right. And you see the dissipation is nearly zero everywhere, apart from those interfaces. Then you form these beautiful Kelvin-Helmholtz billows. And you see just during the evolution, this entropy steering figures out pretty much exactly where the interfaces here are. And in the bulk of the quiet flow, the dissipation parameter is essentially zero. And I think, well, to my knowledge, at least, these are at least the nicest looking SPH Kelvin-Helmholtz tests that I've seen so far from all of what I know. Now, maybe a bit more of an astrophysical test. There are lots of more just purely hydrodynamics tests and very challenging ones in the paper, maybe just a more astrophysical one. This is motivated by a paper from Ilya Mandel and Yuri Levin, where they had found that it could actually be a fair fraction of tidal disruptions that are actually double disruptions, so that you have a binary system flying towards a massive black hole, in this case a 10⁶ solar mass black hole, being disrupted. And I asked him to give me his initial conditions, which he had produced by point masses, and I made a simulation out of this just to show how flexible and robust the code is. You see here the first star has just been disrupted. The second one has also been disrupted. Now they're flying away. And you see, I will now rescale everything so that we are not losing any of the material. So this rescaling has nothing to do with the computational volume. That's just a movie, because of course the particles can go wherever they want. And you see now you form these extremely narrow gas streams. And they're approaching now the black hole here and forming this accretion fan here. And you see, well, roughly half of these stars are still moving away, while the other half is moving towards the black hole. And you see, this is geometrically very challenging, and in particular because these narrow streams, they are held together by the self-gravity of the gas. So you have to do all of this right to get this type of simulation. And I think it's fair to say this is extremely challenging for any Eulerian code that I'm aware of, at least. Okay, I want to stop with this Newtonian type pure hydrodynamics here, and I'll just briefly mention a couple of the recent results for a full GR code. And this is something that has just come out a couple of weeks ago. I think the April 29 or something like that did the paper come out. And the idea here is that we have relativistic SPH, but also evolved the space-time. So it's not just in Kerr-metric, but also evolving the space-time. And I will just briefly mention the basic ingredients and then just try to convince you that it actually works by a number of tests. And these are standard tests for Eulerian general relativistic hydrodynamics. Now, maybe one of the first questions that you may ask, well, why in the hell do we need a new numerical relativity code? I think there are actually good reasons. One of the good reasons is this multi-messenger detection that I had just advertised a couple of slides before. And again, what I had also said before, one of the major information sources was the electromagnetic emission, and this is coming from a small amount of ejecta. And this is really crucial to resolve if you want to get the electromagnetic signature right. Now, why is that difficult for Eulerian code? Well, the first one is that it's very challenging for Eulerian code to have this interface here, that you have a high density neutron star and just outside the vacuum. And what usually you have to do is you have to fill the vacuum by some low density material. And you have to make sure that anything you want to claim is not impacted by the presence of this material around it. But it also means if you eject some material, these ejecta have to move out against this vacuum type material. Another point, which I think is very often overlooked, is this exact advection, which I had mentioned a bit earlier. And maybe just to illustrate what I'm talking about here. So this is a simulation from James Guillochon. So it's just a star in hydrostatic equilibrium. and the star shouldn't do anything. It's just moving with respect to the grid. And you have seen, well, first of all, it has deformed here, and you see you form these plumes, and they're just artifacts from advection not being exact. And of course, these effects, they go away, of course, with resolution, but normally you don't have infinite resolution. And especially for the ejecta, if you follow them on a Eulerian grid, the grids usually become coarser and coarser as you move further out. And then you have such effects really kicking in. And that's why we thought it may be good to have an alternative code which evolves the matter fully Lagrangian, especially since one of the things that I'm really interested in is this electromagnetic emission and the nucleosynthesis that is at the base of it. So, this is, I've been mostly doing this with a colleague Peter Diener from Louisiana State University. And as I had said, the code contains this BSSN in its name, and this is due to these guys here. This is due to Baumgartner, Shapiro, Shibata, Nakamura, Ohara, and Kojima. And what we're doing here is we are just, in a sense, relying on techniques as they are used in Eulerian hydrodynamics. But we also want to model the fluid with freely moving particles. So we have this here on a Eulerian grid, while we have these on Lagrangian particles. And that means they have to talk to each other. And this has been actually one of the major challenges in this whole development effort. And I will not go into the details of that, but just tell you what we have to do. So for these Lagrangian general relativistic hydrodynamics, you can derive this very similar to how you would do this in a Newtonian way. And you come, like in actually probably all hydrodynamic schemes, you have something like a momentum equation, you have an energy equation, and you have something like a density equation, which here for conservation reasons, we use a baryon number for this property that we want to evolve. And the look and feel of this is very, very similar to Newtonian SPH. So you also have the equations look actually very similar. Well, not the problem, but one important difference is, though, the quantities that we are evolving here are not the quantities that we're interested in. So you can write this in a very similar way, but this is not a velocity, but this is something, a canonical momentum. And you need to do a couple of steps that in relativistic Eulerian hydrodynamics you also have to do. And that means you have to recover your physical variables that you're really interested in. So things like the velocity from your set of numerical variables, which just makes the system numerically well behaved. But this is somewhat like a tricky step, but we do this exactly very much the same as this is done in Eulerian hydrodynamics. Same thing with the space-time. There we didn't want to start experimenting again, since there are ways known how to evolve this stably. We adopted these approaches, but actually say our whole code is essentially written nearly completely from scratch. What we're doing here is we're also splitting space-time into three-dimensional spatial hypersurfaces and evolve this further in time. And techniques look very similar to what you have in Eulerian hydrodynamics. And again, here you have something which is very similar to electrodynamics. You have a set of evolution equations, and you also have a set of constraint equations that ideally should be perfectly conserved. So something very similar to the diff B constraint in magnetohydrodynamics. And as I said, we evolved this according to this known BSSN formulation. And now I have to set the matter and the spacetime, they have to talk to each other. So if you want to evolve the spacetime on a mesh, the mesh needs to know the energy momentum tensor at each point, and it's getting this from the particles. While the particles need to know what the metric is, and they need to know also the gravitational acceleration terms, which are calculated by the derivatives of the metric. So these things, well, the energy momentum tensor has to map to the grid, and the metric plus some extra terms needs to be mapped back to the particles. So there are two steps, somewhat similar to plasma physics, but I think we have to be more careful here with the numerical methods because the system is numerically more delicate. Okay, so I just want to leave it here with technicalities and just try to convince you that it actually works. So the first test that you would always do with a new hydrodynamics code is look at a shock tube. So you have some high density, high pressure material here, some low density, low pressure material there. You take out this wall, and then you have a shock wave propagating to the right. And this has a known solution. This known solution is what you see as this red line here. For example, this is for the baryon number density. And you see overlaid is the result of our three-dimensional Sphinx simulation. And you see this agrees very, very nicely, I would say, given that this is a three-dimensional simulation. So from this, you could conclude, okay, at least the special relativistic shocks work. Then we also wanted to know, of course, well, does the coupling to the space-time work? And of course, the first thing you would do is keep the space-time fixed and then let a neutron star oscillate and measure the frequencies. We did this, and this came out very nicely, very much the same as in Eulerian codes. Then you do the next step, which is actually even a bit more challenging, where you evolve both the hydrodynamics and the space-time. This is what we have done here. This is what you see here, times in millisecond. Here you have the central, here you have the central density. If you try to just set up the star, then you see it wobbles a little bit. This is the black line that you see. And in the other cases, we have really excited oscillations and then measured the frequencies in these oscillations. What we found is shown here in those solid lines for different numerical resolutions. And what you see as these dashed lines, these are the results from a Eulerian hydrodynamics simulation. And you see that there's beautiful agreement between those frequencies that we find here. Now, maybe one of the major selling points of our method is that our vacuum is really vacuum. And one question that you would also ask, of course, if you evolve a neutron star that you've set up as good as you can, is does it actually really stay to the solution that you have found with the one-dimensional Tolman-Oppenheimer-Volkoff equation? And this one here, we have evolved this for 10 milliseconds. So it had time to oscillate tinily for about 14 oscillation periods. You see how it looks there. After those 10 milliseconds, the surface is still perfectly razor sharp, I would say. And if you look at the density profile, you see the initial condition, which is the black dots here. And you see the densities of our particles as the red dots. And probably it's hard for you to see a difference. You see a little bit at the outer edge. What has happened is the particles have tiny little bit moved in. But otherwise, this red line is exactly lying on top of the black one. So it stays nearly perfectly on top of the initial condition. Now, a very challenging test, and that's the last one that I would want to show, is you set up an unstable neutron star. So you have, well, you can draw the mass of a neutron star as a function of its central density. And if you're to the left of this maximum here, this is a stable branch where the star should be stable, but you could in principle also set up a star on this other branch here, on this unstable branch. And what happens to such a star depends really on what exactly you do to the system. So it's very sensitive to anything that happens initially. So if you just, well, what the literature tells us, for example, Baiotti and Benuzzi et al. 2010, they find if you just set it up as good as you can and just let it go, then truncation error drives the star into violent oscillations. This is what you see here. But it moves over to the stable branch. But on the other hand, if you give to your star a tiny little radial velocity, and we're really talking here about 0.5% of the speed of light, then this triggers, contrary to this one, this triggers the collapse to a black hole. And we wanted to know, can we confirm this? And so this is now the best possible setup that we have. And you see, this is exactly what our Eulerian colleagues have found. So the star undergoes very violent oscillations. And actually here you have velocities. It's really violent. So they have of the order 60% of the speed of light. And here we have, well, varied again a bit the resolution and the finite differencing order. But you see, we get something very, very similar to what our Eulerian colleagues have found. And now the other difficult part was now take exactly the same star, but instead of just letting it go, you give it a tiny radial velocity perturbation. And this is what you will see here. Now I'm showing just the particles. You see the star actually really does start collapsing. And at some point in the very inner part, we're starting to remove particles, and then the whole neutron star is kind of eaten up by the forming black hole. And again, this is in very, very nice agreement with standard numerical relativity tools which use Eulerian hydrodynamics. So maybe just to very briefly summarize this, I guess in this crowd, I don't have to say this because you're also excited about this stuff. So I think multi-messenger astrophysics is really one of the best areas to work in, probably throughout a fair part of the 21st century. And it's really has begun to bring together lots of different disciplines, from really transient astronomy, general relativity, nuclear physics, neutrino transport, you name it. And I think there are really good prospects to solve many puzzles that were around for a very long time, and hopefully in the next decade or so. And with that, I want to stop. Thank you very much for your attention.
Thank you, Stefan. Then we're going to start with the questions. Please, Enrique.
Hi, so very nice talk, Stefan. Thank you very much. So I know that our Eulerian friends over here are feeling overwhelmed, probably. So trying to level the field then a little bit. So when can we expect to see from your group SPM? Because it's one of the important ingredients in these things, right? You also have a very large magnetic field, which has relevant effects, and I don't think that's included in your codes yet, right?
No, it is not. Say we had in an earlier Newtonian version, we had done this, and by means of something which is called Euler potentials. But I think, well, I think you can get it to work very well, but just by the Lagrangian nature of SPH, there are some topics where I don't think you have a chance to resolve this. And this is just where one of the major advantages of SPH turns into a disadvantage. And this is just that the particles follow where the fluid is going, where the density is going in particular. But in many cases, it's really just interesting to see where the field is strong. Say, if you want to form a jet, this may happen in a ridiculously low density region. And this is where you will not have any resolution. Then you could say, well, maybe since you guys are evolving anyway, your space-time on a mesh, maybe you can do the magnetic fields on a mesh. And that is, of course, a natural thing to think about, but that may probably get rid of some of the advantages, because one thing why we get away actually relatively nicely with the space-time is that the space-time is very smooth. So that means even with a relatively coarse grid, we get a pretty good representation of the space-time, especially if we do this with higher order finite differencing, and we can just invest our computational efforts into the particles. But if you now want to do magnetic fields, then you need an adaptive mesh which really focuses on the region where you have shear layers or whatever. Then all of this is gone. So that's why for now, I will not tackle it. And maybe as a side remark, I think especially in this neutron star merger context, I think it is extremely difficult to get the right answer. I think we all agree, just from basic physical considerations or from existing numerical simulations, that pretty much whatever you do, the field must grow. And but whenever you double your resolution, you get a higher field, because what grows are the shortest wavelengths. So something like in a Kelvin-Helmholtz stability, the perturbations. And this is what determines then the field strength in the end. And that means whenever you do this better, you get a higher field. Then you can wonder, well, where does it stop? And well, of course, it stops somewhere where the magnetic field becomes dynamically important. So where the magnetic field pressure is comparable to the matter pressure, and or some fraction of that, maybe 10% or so. And these are, of course, enormous field strengths. So this can be 10 to the 17 Gauss even in the core of a neutron star. But I don't think you have very realistic chances to get this right. And that's why we are at the moment focusing our efforts on other things. Although I agree, in principle, this is something that will happen. And some aspects may be impacted by that.
Okay, thank you.
Aldo?
Give me a second. Yeah.
Yes, you're unmuted now.
Yeah, I am now. I'm not starting the video because my Wi-Fi is kind of shitty over here. So beautiful work, Stefan. I wanted to ask you about the Sphinx code. What about the initial conditions? You have to do also a relaxation of initial conditions in this case?
That is a very good point. And that is something that we are currently just working on. The tricky bit which makes the fully relativistic simulations much more complicated than the Newtonian ones is that the initial conditions are even more complicated because on the one hand, they need to represent physically what you really want to simulate. And on the other hand, as I had said briefly on one of the slides, you have evolution equations and constraint equations, and you have to satisfy the constraint equations. Otherwise, you're solving something which is not really controlled. So, this is really a bit of a tricky thing. There is one library which is called Lorraine. I don't know whether some of you maybe know this. This is from the group in Meudon. But this has been done for Eulerian codes, and we have started to work with this and translate this to our particles. So this is ongoing work, and we have the first mergers are running, but there's still a bit more work that we want to do. And very closely related to your question about this relaxation step, that is very important for SPH. I think a lot of the quality of a simulation depends really that the initial condition really is what you think it should be and not just a rough approximation to it. And for that reason, you need to place the particles in kind of an ideal way. And this is actually pretty challenging. And for the single neutron stars, I've developed this for Magma. I called it something like, which is called the artificial pressure method. It's some way to drive the particles in the positions where they should be. And we have done this also in the GR version, but so far only for single stars. But at the moment, we're doing this for binary stars. But if we are just happy with setting up particles on lattices and letting them go, that is working. And yeah, that's part of the stuff that we try to fix the last details right now.
Okay, thanks. One more thing, is Magma 2 available for people in general?
Not at the moment, because one thing we would want to do is to improve the parallelization further. So at the moment, it's only OpenMP parallel, but to say that also, and I don't know, those of you at least who do SPH simulations have probably a feeling for what these numbers mean, but at least I have done some tests with 100 million particles on just one single node. So it's pretty well optimized, I would say, for a single node, but the multi-node parallelization, that is stuff that needs to be done first before we make this public.
Good. Thanks, Stefan.
My turn. Perhaps it's a very naive question. Do you expect that all kilonova to have the same behavior? I mean, do you think that the kilonova that we saw 4 years ago is representative? Or what parameters do you think that could change in your models related with the mass and composition of the neutron stars involved?
I think this is a very good question. And it's of course a question that we have thought about and other people have thought about as well. Of course, we don't have the final answer, but part of the reason why I call them macronova and not kilonova is exactly what you're asking. So astronomy is full of misnomers, things that have been names that have been given before the things were understood. And the kilonova, of course, implies that these things are 1,000 times brighter than a nova. and I don't think we know this yet. We have one event that is well known. And as I tried to show with our jet simulation, these seemingly tiny little details of 10 to the -5 high neutron richness outer layer can make a difference to the electromagnetic appearance. And I really think that is another thing which I'm not sure is always appreciated enough by, especially on the observational side, that this mass that has been inferred for this kilonova is really gigantic. So when we had our first results on ejecting material, people were calling us completely crazy because we found something like 2% of the solar mass, and people were thinking of 10 to the -5 or so. And they were thinking we are completely crazy. Now that thing that has been found the estimates are maybe 7% of the solar mass. So it is a huge amount of material. And this may be very system dependent. I think if the merger leads pretty much immediately to a black hole formation, the amount of mass would be much, much lower. And same thing for neutron star black hole cases. To get a substantial accretion disk, you need to have the right system parameters. Many neutron star black hole systems will not give you a disk, or not a disk that has any interesting mass. So many of them will just more or less just shred the neutron star, eat it up without forming a disk. So I would really think results are probably very sensitive to the exact thing that is merging. And therefore, I would really expect that there should be a huge variety of those guys. And I'd be more than pleased if we find more of them. Let me be very honest, say in 2017, I think we were all super stressed when that thing came out, and we were working day and night to get all these Nature and Science papers out. And then after that, I was actually, well, didn't feel too much sorry that there was none immediately observed again, but now it's a couple of years ago, and I think we deserve now a couple of more. And I'd be more than interested to see how new ones would look like. But it could really be that this was a particular event. Same thing, like I think when the first real multi-messenger event was seen, the supernova 1987A with neutrinos and photons, astrophysicists were also extremely excited and hoped to see that again and again, but it hasn't happened since 1987. So let's hope it's better for these macronovae or kilonovae. But we don't know. It could be that this was really just a lucky event that had the right system parameters to eject a lot of material, was nearby, was also detected. So it could be that this was a rare thing, but let's hope it's not. Say, the initial estimates were up to 10 of these guys per year or so. And yeah, now we don't know. So it could be substantially less, but we don't know. But I would think it was a special event.
Thank you. Emilio?
Okay, thank you. Well, first of all, thank you, Stefan, for the talk. It was very interesting, all the update. I just have a question regarding these new simulations with the Sphinx. Do you think it would be simple or feasible to tackle both a self-gravitating star and a supermassive black hole for tidal disruption simulations?
That is a very good question. Exactly, for some things that we have been thinking about a couple of years ago. I think it will still be very challenging because, say, especially the tidal disruptions, for very nearby flybys, solving for the metric will be very tricky, I think, because the star is still just a tiny perturbation of the background metric from the black hole. And that would probably mean you need a very, very, very large resolution to get just this tiny little extra dip from this Newtonian star as it's perturbing the it's perturbing the black hole metric. And then as it's moving away from it, then you see in all these Newtonian or pseudo-Newtonian simulations that depending on the impact parameter, self-gravity can kick in again. And this is then the stuff which I think is then getting impossible, and for the same reason as in a Eulerian simulation, because if you really want to simulate a large volume and you really are not happy with a fixed metric, then you have to resolve very small length scales as you move away from the star. And then you have the same problem that a Eulerian simulation has.
So
If
you would say it's still a challenge?
I think it's still a very big challenge. I think we have, well, the good thing is for many of the cases where you don't have to resolve such a self-gravitating small core or something, you can probably switch from a dynamical metric to a fixed metric at some point. And this is something that we're also experimenting with, but as always, the devil is in the details, and it's much more difficult than you would think initially. So for some of the cases, we can actually do this. Let's then maybe just evolve the space-time in a restricted fraction of the space, and then outside of it, maybe you smoothly blend this with some Kerr metric or so. And this may be a very good approach for many things, but for some of the things that I think you are thinking about in tidal disruptions, some of them would have the same challenges as Eulerian and would be very hard. So, and the other thing is, the other thing that you have to keep in mind, it's expensive. The space-time evolution is really, really expensive. So, but maybe, yeah, maybe that's another thing, something we had thought about also ages ago. Maybe the full space-time evolution would not be the right approach for this. But one thing that one could maybe think about that would be doable is something like a perturbed Kerr or something. If you could get extra terms, maybe some elliptic terms or so, and you have then some elliptic solver on top of that, that would be something that maybe it's actually accurate enough, likely I would think. But this would probably be more promising than really doing it brute force.
I see. Well, probably I can email you later and we can catch up with this.
Okay. Okay.
Okay. Well, thank you.
Diego?
Boy. Cool. So can you put the plot in which there was the galactic abundances? I mean, I have like a really naive question.
Wait a second, if I can find the share screen button, which I think.
But yeah, we can see it. Just if you put slide number, I don't know, 10, 12, it was like nearly at the beginning.
Okay. You tell me once you see it. Which one? Not this one?
No. When there,
This.
yeah, that one. Okay. Or the one that you have your video. So here, I mean, it just seems counterintuitive that the heaviest elements are produced by the S process. I would have expected like the two heavier spikes to be the R and not the other way around. Like, what is going on?
That's actually a very good question, but let me just see. I had this for some other talk where I tried to explain this. So what, can you see this one here?
No, we're still seeing the same presentation.
Oh, okay, then I have to stop sharing. And then, wait a second, this one here, then I do share screen. So this guy here. Is that better?
Yeah.
So that's actually a very good question. And say what you see with these peaks is actually the impact of those magic numbers. You have something like closed atomic shells. In atomic physics, you have in nuclear physics these magic numbers. So this one here is at 126. So that means nuclei where the neutron number is 126 are particularly well bound, and they don't want to capture new neutrons. And this is now exactly the reason why you have these two peaks. So if I may just with the mouse show a little bit, you have seen for these tidal ejecta, all of the action was happening here at the drip line. And you see at some point you're encountering here close to the drip line that magic number of 126. And as I said, once you're there, the nucleus doesn't want to capture any more neutrons. And that means you pile up lots of nuclei there. And at some point, your explosion is over, the merger is over, or whatever explodes. And then you just have these very unstable nuclei decaying, and beta decays go up this diagonal. So if you pile up material here and you decay back to there, then you end up producing a peak at this position. You can now do the same thing, but you're just much closer to the value of beta stability. Say if you are in an S process, say somewhere here, then you would decay from here, and then you end up to the right of the R process peak. So this separation just tells you what the interesting bit, I think, is that you really see in those R process peaks, you see the magic numbers. Maybe you can see this actually, in this plot even a bit more. Say there are 3 of those R process peaks, and you can connect all of them to magic neutron numbers. And say just what we had talked about, the one being to the right of the other, just tells you how far away you are initially from the value of beta stability, but trapped at one of those magic numbers.
Okay. And I have another really quick. So what I didn't quite follow is when you put that beautiful Kelvin-Helmholtz simulation that you're able to have like those really nice swirlings. What is the take a home message? Like, what is the one big difference between your SPH there and the others? Like, is it the kernel or what was it?
This is another very good question. And we have, I guess you can see that now.
Yeah.
Again. So yeah, it was this guy here. So yeah, this is one thing. If you go to the magma paper, I had actually looked, I stepped ingredient through ingredient to see how big the difference is. And this one here is, of course, well resolved. There are many things work nicely anyway, but I did these tests at a low resolution so that I really see the difference where things kick in. And well, I'm not sure, I don't think I have it here now. Well, maybe I can open another one. Wait a second. I talked about this at some point. Maybe it's here, this one. Yep. Can you see this one, or have I just clicked again, just one screen? I guess I have to stop.
Yeah, we're seeing the same.
Yeah, then, okay. Now I have to, now I go to this guy here. Do you see that one?
Yep.
So here I look at just different ingredients, and I've just changed. One thing is our default at low resolution, and you see nearly everything gives a good, well, or at least an okay Kelvin-Helmholtz instability. But the one thing that really is the killer in this application is this one here. There you see this is one case where no Kelvin-Helmholtz grows. And this is the case without the reconstruction. So these finite volume techniques, they really, really help. So in this case, the best thing, of course, is if you use all of the bells and whistles. But if you want to know what is the one thing that makes the difference, in this case, it's this reconstruction in the dissipation term.
Okay. Very nice. Thank you.
And finally, Felipe, please.
Hello, Stefan. I am Felipe. I'm Fabio's student. And my question is a little bit similar to Diego's, but I would like to know what are the main difference in relation to Eulerian codes. Do you think it's easier to code? Do you think it's easier to make one of these codes in relation to an Eulerian?
I'm not sure you're talking about writing such a code or applying it to astrophysical problems.
Like writing the code, creating.
I think I don't know. I've been from scratch. I've been writing only particle codes, and I've only been writing one-dimensional Eulerian codes. And I think they all have their pros and cons. But you have I think you have a couple of subtleties with SPH that maybe you don't have with the Eulerian code. And if you're not aware of them, then you may be struggling getting things really right. And one thing, just from, if you're interested in also performance issues, one thing that I think is relatively straightforward is getting good performance in a Eulerian code, because first of all, the parallelization and the load balancing may be more straightforward because you can just split your domain in probably very much an intuitive way. The other thing, which is less obvious unless you do a lot of simulations yourself, is your Eulerian codes. What you're normally doing if you do some finite differencing, you're always touching a grid point and the grid points next to it. And that just means for the computer that it's touching memory that is very nearby. So you will touch one grid point at the one nearby, which is also nearby in memory. And that means that stuff is very likely in cache, and therefore without doing terribly much, you will have a very good cache performance. While in SPH, whatever particle is close, if your particle 21 is close to particle 22, that may be right in your initial setup. But this is something that you could potentially see if you let it just run. In the end, your particle 21 may have particle 10 million something next to it, and that is very far away in memory. And that means sometimes if you're swirling around your particles, you see that your code starts becoming really, really slow. And exactly for this reason, that it's continuously grabbing data from very slow parts of the memory. And of course, you can do something about it. You can reorder your data structures and sort particles, and you can do all kinds of things that really help a lot. But this makes it pretty tricky to keep the code readable, because then you can make it really, really unreadable by all kinds of sortings and listings and pointings and whatever. So I think in some respects, writing it can actually be a bit more tricky for a particle-based code. But since you're working with Fabio, I don't know. The last time I talked with Fabio, he told me about, I think you also have some Voronoi tessellation type code. That may be yet another thing that may be probably more complicated than a normal Eulerian one. But that's maybe up to you to answer. Or which code are you working with?
I work with Mescal, but
Mescal.
Eulerian.
Which is Eulerian, yeah, but it's not. Yeah.
But it's finite, it's Cartesian adaptive mesh refinement, is it?
Yeah.
Okay. Can I then ask, say this? I think this Voronoi tessellation code we talked about, at some point, I guess that was probably also, I don't know, in Cambridge at one of those conferences a few years ago. Has this been published at some point?
No, still developing it.
Okay.
After 4 years.
Well, I say I had a couple of codes that took way too long, but that's how it is in normal life sometimes.
Yeah. So about it, I make a question. So just how do you compare a Voronoi, I mean a moving mesh finite volume with SPH? Because you were talking about the problem with advection and the other problem.
I would think I think it's getting down a little bit to a question of nomenclature, how you call codes. Say mine is now formally still SPH, but has a lot of finite volume ingredients. And I've actually, another thing which is also not published, I've also made a finite volume code, well, a pure finite volume code, but also on particles. Say finite volume methods are also not restricted to grid cells. You can also do them on particles. And I think they're getting similar performances. And when I did this Magma paper, I really wanted to exactly tackle those problems where people say these are very challenging problems. Therefore I wanted to show that you can actually do them. And but I think it's overall the performance is probably very similar. I don't know, maybe the finite volume codes can be a bit faster, because with my Wendland kernels, I need lots of neighbors, and therefore just calculating density and gradients costs. But I can also maybe show some, well, if you allow me to share the screen one last time. Maybe this guy here. So this is another set of tests, which maybe one of you has done this, but I think I've only seen this for one SPH code, and these tests are called Schulz-Rinne tests, and they are super challenging. There you have 4 kind of tiles, and the initial conditions are tuned in a way that you create shocks and vortices. And maybe just one example is this particular Schulz-Rinne test, where you then have this bizarre looking shock going inside, and here you have this vortex with this sharp shock front here, or this one here, where you form these beautiful crispy vortices. And I had just seen this in one paper with an SPH code with a Riemann solver, and that did not look very nice. And these ones here, I think they look very, very similar to very good Eulerian codes, which seem to have an easier time for this type of stuff. So, but for Fabio, I think these are very nice methods, these finite volume particle methods. But I guess they would probably be in the performance, they would give very similar results. Well, maybe to qualify this a bit further, I had compared my magma results for these blast waves, for this set of Taylor blast waves with the results from the Gizmo code. And Gizmo, if you know that, and Gizmo looked much, much more noisy, but that is probably because I'm using lots of neighbors and they're just looking at the nearest neighbors, which produces a lot of noise if a shock goes through it.
So it's a little bit more tricky to adjust the SPH code, and finite volume codes are more standard, let's say, no? Well, SPH have to.
Yeah, I don't know. Say, I had recently given a pure hydro talk, and there I tried to explain how reconstruction works in a finite volume code. And then when I explained it, how I do it in SPH, then I thought, well, in hindsight, it's actually pretty obvious. And I'm wondering why this hasn't been done earlier. So it's really like you have a jump between 2 quantities, and you can just take the jump at your cell centers, or in my case, the particles, or I can reconstruct the jump to the interface, and then the jump is much, much smaller and you dissipate much, much less. And in hindsight, it's obvious. And I think it's similar. I guess the gradients are a bit more complicated than just finite differencing, but I think that's the only difference. Otherwise, from the idea, I think it's pretty similar.
Okay, thank you.
Okay, then I think that we
you.
can finish here.
Okay.
And please turn on your camera just to say goodbye. Thank you very much, Stefan. It was an excellent talk.
Okay, thank you.
Goodbye.
See you next week.
Bye.
Bye.
Thank you.
Thank you.
Thank
Bye.
you.
Bye-bye.
Ciao.
Bye.